good. For online participants, just wanted to update you. We are getting some people through the registration desk, and so given the weather, we're going to wait a little bit longer for some more participants to arrive. So if you can just stand by, we'll be with you shortly. Thanks.
There should be. It's on now. Is there sound? Okay. All right, everybody. We're going to get started. All right. So I'm Kenrick Mock. I'm the interim dean for the College of Engineering, and welcome to our Journey into Engineering Night. So you may have heard we had one of these scheduled yesterday that we ended up canceling because of the snow. So today we have demonstrations about computer science, computer engineering, and electrical engineering. But if you're interested in civil engineering, mechanical engineering, geomatics, or project management, that's a graduate program, so you have to have a bachelor's degree to go into it. But we do have a minor in project management. If you're interested in those, then come next week, same time, a week from today, and we will have a week from yesterday. Sorry, thank you. So a week from yesterday, so Tuesday, come and learn about our other engineering disciplines. So, just real briefly, I've already mentioned the different programs that we offer. The College of Engineering has been around in some form since the 1970s, and so geomatics was actually our first program. One of the things we run into is people don't know what geomatics is, and that we're thinking about changing the name to geospatial engineering. So if you think about maps and drones and 3D imaging, that's all about geomatics. So we have, if you're interested in a career in engineering, hopefully you get something good out of what we're going to show you. We have some professors here that you can talk to and ask any questions. We also have students around that you can ask questions about what it's like to be a student here. I can say a little bit about our graduates. They get jobs real quickly. We have some statistics that around 70% of our graduates work in Alaska, and the vast majority of them get jobs right away after graduating and do some amazing things. You can't see it right now because these blinds are moved over, but that bridge over here was designed by one of our graduates. So they are placed all around the state. So without further ado, I am going to turn it over to Vicki, who will break you up into groups and get this show rolling.
Thanks. Did you? Yes. Did you explain the microphone thing?
I didn't.
No. Okay. So my name is Vicki, and for those of you who are looking at, let's see, what do we call you, Dean Mock? As if he was crazy for speaking into a microphone that's not amplifying. I just want to go ahead and explain that to you. We actually have online participants. We're streaming online as well. So this microphone is not intended to amplify, but is actually helping us relay good audio to our remote online participants. So not crazy.
Might still be crazy.
Maybe, but not for this reason. Okay. So welcome. I'm really glad you guys all braved the roads. I hope you drove safely and you drive safely home as well. Thank you for coming here tonight and joining us. We were originally going to send you around in 4 groups, but it looks like a great number of our RSVPs did not brave the road, so good job to you courageous folks. And so we are actually going to merge a couple of your groups. Yellow is a large group and is going to stand on its own. So if you were assigned to yellow, you will remain as one yellow group. And we are going to combine orange, pink, and green into one group. And so let me introduce your group leaders to you. We've got Nicole, who is an academic advisor for the College of Engineering. So if you also, while you're out traveling with her among your stations and interacting with computer science and electrical folks, you're welcome to ask your advising questions of Nicole. Next to her, we have Emily, which if you recognize a resemblance there, that's because that's a mother-daughter duo. She is a computer science student in our program, so you are welcome to ask her questions about what it's like to be going to school here. Then we have Laura next door to her. So Laura is an engineering student and also French major. She is a great resource of knowledge. She's also a student. Cooper is a recent alumni, so he just graduated from our mechanical engineering program. He is offered to help out as a tour guide as well tonight. And next to that, Joe Selmont. He is staff here. He is the director of our summer engineering academies. So all good resources to ask questions of as you go between our stations. We have faculty in different labs and classrooms excited to show you demonstrations in both disciplines this evening. So They are professors who, if you choose to come to school here someday, will be the ones teaching you. So feel free to pick their brains as well. Your group leaders there know where you're going. Yellow group, you can steal someone and take them with you if you want. And then pink, green, and orange are following which track? Orange track. Okay, cool. So yellow, if you want to raise your hand, Laura and Cooper. Okay, so Laura and Cooper will be taking yellow, and we will actually not be able to reconvene here at the end because there's just so many cool things to see up in the labs. So if I don't get a chance to see you again, I want to thank you for coming, and then yeah, pick their brains and enjoy your demonstrations today. Thanks.
Testing, testing, 1, 2, 3.
And then when you do that, because Bitcoin's a public ledger, you'll be able to see this pop up on the blockchain. So I urge you to check out all these things and just ask me any questions as you check out these different stations. So, thank you.
Thanks, Evan. So yeah, it's kind of a hands-on experience here. So if we got a couple people that want to play Pong, step on up.
I'll reset it here.
No pressure. I mean, I'll play. Does anybody want to play with me?
Go ahead.
Yeah, come on. So this just goes.
You have a center button here.
That's you.
And like A is dot long. So I just put it in
What
an
was
A.
your name?
If you pause too long, that's a space. So if you want to have things happen one after another, you have to be
Junior.
quick.
Nice.
Any takers for the candy?
I'll guide you guys through it. So you just have to download it's this BitPay app, and you scan this code, and then you'll have Bitcoin after it too. Cool. I think I loaded this before. There might even be 20 cents on this at this point. price is so vaulted.
So you're thinking about candy? You know what type?
So how long has Bitcoin been around?
It started in 2009.
How has it grown since then?
It's grown. I mean, it's grown a lot in popularity because people have heard about it now, and like along with that, the mind share of the price has also risen. But it's in terms of its size, like the actual like data structure is only like 100 gigabytes, so it's relatively small.
What do people use it for most? Large purchases?
Does anybody else want to jump on
So
here?
like Bitcoin right now,
Spend that.
and for the regular Bitcoin
Fancy little.
sort of network, transaction fees are pretty high. So if I pay you $1, 50 cents of that are going to go to the miners as transaction fees. And so because of that, it's only really useful for larger purchases. Like even spending $100, I don't want to spend
Well done.
like 0.5% on 50 cents on it. So for like $500 and above, I say it's relatively useful, but no one really accepts it yet, so it's a questionable use in the first place.
Do you see it getting more mainstream with things like Apple Pay and the online?
Oh, it's probably Bitcoin was cool like 10 years ago because before it wasn't really possible to pay someone on their phone from one phone to another. But now with Apple Pay, that's kind of eating Bitcoin's lunch in a way.
Okay.
And so it's probably hurting this payment system. To use this, you have to go to the store and download the BitPay app.
Anybody else want to give it a shot?
How many of you have ever heard of Pong before? Okay. Don't feel that dated.
That's a good point. I may have made a game that
That's a classic,
may not be
though,
familiar.
but it's classic. I think everybody should know Pong.
Yeah, who doesn't love arcade games?
Yeah. It's like Pac-Man.
The score is even kept down there on those LEDs.
We got just a couple more minutes here, so if anybody else wants to try this stuff out, last chance. Until you're a student, anyways.
Yeah, everything that you see, well, except for the candy machine. The FPGAs is stuff you'd actually be doing in some of the classes if you came to the CS department. So we will do a project doing Morse code and doing sending signals and making, at a very low level, these simple games on this board. So.
And then you'd be like, look what I made. It's a nice feeling, and a good interactive one as well.
Yeah, awesome. Well, thanks a bunch, Seb, Dr. Newmeyer.
Yeah.
Yeah.
Good seeing everyone.
That's great. And now we are gonna mosey kind of just down classroom, I think, to EIB 316, where we're gonna learn a little bit more about robotics.
All right. Okay.
Trying to leapfrog with parts since everyone's on one track.
Hold up the board.
We're just gonna unplug and plug back in 316. So let's go. I got it. Thank you, sir. hand the mic to him for me.
Oh, sure. So this will just be to communicate
Got it.
to our online folks.
So we're working to restore a couple of videos that we were hoping to show you, as well as a slideshow just talking about what it is we do at UA Robotics. So UA Robotics, we're an interdisciplinary club whose primary goal is to get practice manufacturing, designing, and building upon robots like this one that you see here. This one we call Iceberg 3.5 because it's a sort of an upgrade from last year's rover, which was known as Iceberg 3. And he's got the SAR video shown up in just a few moments. We'll get to this, but I also wanted to introduce Tyler here. He's do you want to?
Yeah, hi, I'm Tyler. Are we using the? Is this? Oh, okay. Hi, I'm Tyler, and I'm on the electrical engineering team. So, welcome. We'll go ahead and get started and play the video we've got for you. So, is there anything we want to do for the online people? Speakers. Yeah. Okay. Yeah.
Entering our third year with support from UAA and many professional organizations, our team of over 30 students chose to iterate upon and optimize last year's design. Introducing Iceberg 3. UAA Robotics divided into teams dedicated to each rover subsystem: mechanical, electrical, software, science, and project management. We developed a Gantt chart and task list based on challenge requirements and available resources. By utilizing FEA on mechanical structures, 3D printing, and industrial machining equipment, we rapidly prototyped and optimized new design features. As supplies were purchased, we built, troubleshot, and tested systems in parallel.
Chassis and suspension designs are centered on the extreme retrieval task. Our four-wheel independent suspension system is designed to traverse any terrain with ease, including the 1-meter drop. By utilizing a bulkhead design stiffened with steel rods, we created a small, light, and sturdy chassis. Coupled with our 400-watt brushless DC hub motors, the rover has a low center of gravity and impressive agility.
The rover runs on one 720-watt-hour lithium-ion battery, providing ample power for each competition task. 5 cameras face in various directions to give drivers sufficient visibility at all times. These provide multiple close-ups of the end effector and wide-angle views of the arm and rover. The rover uses a set of 900 MHz ubiquity radios to carry multiple video streams as well as rover commands, allowing maximum propagation through obstacles. A pair of 5 dBi dipole antennas are mounted high on the rover, while the base station uses a 120-degree directional antenna with a 13 decibel gain.
The base station runs a custom graphical application built with WX Python for viewing rover camera streams and monitoring and controlling the rover. It features a navigation system to display the position of the rover in real time from transmitted GPS coordinates and a configurable control system, enabling operation of the rover with a pair of gamepad controllers. We focused on improving our computer vision and navigation software for the autonomous traversal mission. During navigation, the rover uses an onboard GPS and accelerometer magnetometer to precisely determine its position and orientation. OpenCV analyzes the image and depth data from a stereoscopic camera to detect obstacles and hazardous terrain and identify competition markers. Our pathfinding system uses a record of encountered obstacles to calculate the most direct path to waypoint coordinates.
The arm design drew inspiration from a number of industrial sources. The shoulder is powered by a 200-pound linear actuator, minimizing any moment forces in the upper arm. The elbow uses a 30-to-1 worm gear transmission that provides smooth, predictable motion and over 100 pound-feet of available torque. This design allows the forearm to be offset from the upper arm to gain 360 degrees of freedom. We elected to use a worm gear on the wrist along with a unique end effector design that is able to rotate continuously without the use of slip rings.
The end effector utilizes a gripper and a screwdriver system to accomplish the extreme retrieval and equipment servicing tasks. 3 DC motors and a linear actuator provide a clamping force of 13 pound-feet and a range of 2.5 inches with precision control of 907 inch. Paired with the robotic arm, the end effector has a 5-axis range of motion. The main axis is controlled via a worm drive gearbox, minimizing power draw. A 3D printed enclosure prevents dust from entering the gearbox and belt drive systems. The replaceable pads on the gripper are designed for versatility, allowing the rover to grip items, enter commands on a keyboard, and operate a joystick. Both Phillips head and Allen key screwdrivers are mounted to the end effector and operated by the same motor to save weight. 2 cameras provide first-person views of the jaws and screwdriver attachments, with 3 laser pointers to aid in operator control.
The science plan encompasses a combined approach that includes visual observations, an array of sensors, and wet lab chemistry to identify signs of life. A camera scans the area for the presence of animals, metabolic wastes, tracks, microbial mats, iron staining on surfaces due to microbial metabolic activities, and fossils. Rocks and minerals are observed for signs of endolithic organisms. Soil samples are analyzed with a variety of sensors including spectroscopy and gas detection, and added to a luminol mixture to observe luminescence levels to determine the presence of oxidizers, including hemoglobin, protein, urine, feces, copper, or iron. The commercial off-the-shelf D&Easy Power Soil Kit consists of 6 different solutions that purify the soil samples. Then it is tested using a nanodrop 1000 spectrophotometer to deliver a reading of DNA concentration, DNA purity, and nucleic acid purity.
This concludes our 2019 URC SAR submittal. We appreciate your consideration and look forward to seeing you at the Mars Desert Research Station.
Awesome.
So as you can see from our SAR video from last year, how much work really goes into making just this one rover here. It takes the collaboration of all 4 of the different teams to really create one product, and they've all got to take into consideration the pros and cons of what every team is doing and see how the outcome of anyone's project may interfere or help improve anyone else's design. And
Great. What have been the biggest challenges this year?
That's a good question. Well, last year we did have a lot of resourceful people graduate, and for one thing, so we have experienced somewhat of a shortage of people who are able to come in and devote some time into the rover. But following some recruitment processes earlier last semester and somewhat this semester as well, we've recruited a good handful of new people who are coming into, who are eager and willing to learn all the different ropes of just learning how to cooperate, work as a team, and work together to build this rover. And not everyone really has to be a master at their skill set. The most important thing is that they come in willing to learn and are excited to learn new things. Yes? So the Robotics Club is a... So you asked why someone would want to join robotics, is that right? Or clubs or clubs. So if you're able to find a club that's like us, like UAA Robotics, that produces something of value, that makes you stand out on a resume to job employers, because it shows that you've contributed to making something like a rover if you joined UAA Robotics, or if you join some other club. Like I think there's a rocketry club on campus that specializes in rocket design. I actually don't know what they do, but they also they also do produce something themselves.
They launch
so.
rockets.
Oh, they do. Oh, that's pretty cool.
For all your controls to this machine, did you design those controls, or did you take a manufacturer voice recognition or whatever you used to control it? Did you design your own, or did you borrow from here and there and put them together?
So it's kind of a combination of. Oh, I'm sorry. So the question was, do we use kind of off-the-shelf equipment, or do we design our own? For the first few years, it's mostly been off-the-shelf parts. So, like if you were to actually look in there, you would see a lot of computers and power systems and motor controllers that are just basically black boxes that we plugged into each other.
In the past year and a half, though, we've kind of started moving towards building and manufacturing our own equipment. So, like all of the structural components are custom made for the main chassis. And then from the electrical point of view, we're actually starting to manufacture our own printed circuit boards. And we've got several people in the club who are interested in our kind of taking that mantle over to help continue developing custom hardware.
I was just curious where the rover last was. The red dirt doesn't look very Alaskan. Did it get to go stay somewhere else?
Do you want to answer that one?
Yeah. So so someone asked, "What is this red dirt that's on the tires of the rover?" And the answer to that is, last summer, we got the opportunity to go and compete in Hanksville, Utah, for the University Rover Challenge at the Mars Desert Research Station in Utah. And so driving the rover all around, there was a bunch of, I want to just call it red Utah dirt. That was that's supposed to simulate sort of similar terrain that you would see on Mars, and hence the Mars rover competition. Yes.
Can you explain how many colleges usually get accepted into that competition?
So I believe the best 36, I believe, colleges around that number are the ones who are selected to come, who are invited to come compete in the University Rover Challenge, and the requirement for that is that they submit an SAR video like the one that you seen, ours that you saw here. Every college has to do that to be considered to come and participate in the competition, and the best 36 are the ones that get to go, and we were among those 36 last year. So, pretty cool. Any?
What fields of engineering students do you recruit from? Do you look for students that are in different engineering disciplines, as well as outside disciplines that can help with marketing?
Okay, so she asked what engineering discipline students do we recruit usually, and pretty much just about all of them: mechanical, electrical, computer science, and to some extent civil engineering, because the civils are able to help with the mechanical in some respect. Because like you saw in the video, it takes a whole team of people of all different disciplines to help create a rover. So of course, so yes, we do see all kinds of students in different engineering disciplines. Yep.
Have any funny stories about being a part of the robotics clubs with your fellow students working on this rover?
I laugh because I can't really think of any. But,
Very serious, studious club members. Yeah.
So, are there any more questions?
Do you guys have any intention of working in robotics past your university experience?
So for me, kind of my goal for the industry I want to get into is a little more broad. I'm particularly interested in working on like integrated computer systems, so building circuit boards for computer systems. And a big part of robotics is control systems and highly embedded computer hardware. So that's definitely a path I could see myself going down, but it's really a matter of kind of where the job market's at and kind of who is hiring at the time. So, did you want to?
Sure. So I still come to this club every week because I like learning what they do and everything about robotics in itself. But the kind of work that I was wanting to pursue doesn't have so much to do with robotics. The kind of work was more the math side of computer science, so things like machine learning, data science. A lot of the more math-heavy subjects in computer science is what I want to do. But things like the autonomous component in the rover will only help with that, because there's all kinds of algorithms we could implement to make the rover do things on its own, like traverse throughout the whole research station on its own. So we would need to figure out what kind of algorithm or what kind of computer program do we need to come up with so that the rover can do all of that. So
If you want to include the civil engineers, they can come in and help you get the dirt off the floor.
that would be nice. Yep.
So I noticed that you have a lot of equipment around the room that, so I was wondering, does the robotics club give you opportunities in operating machinery that you typically wouldn't experience um, being in your current degree? Like, what opportunities do you get to be given or learn in the robotics club that you wouldn't usually find out during the day?
So what opportunities are we given just being part of the robotics club? I don't know of too many off the top of my head, but I can tell you that for one, the University Rover Challenge and also a lot of sponsorships from other companies that we may reach out to sometimes help us out in achieving that goal.
Yeah, do you
So.
get to work with the fabrication lab much? With like Corbin?
Do we do that?
So
I actually don't know the answer.
Yeah, so the question is, do we get access to the fabrication lab here at UAA? And the answer is yes, we do. I'm electrical and he's computer science, so we don't actually have access to that kind of stuff. We don't really use it for what we do, but yeah, but like this entire end effector was milled out by hand by Corbin, so we often work with him on getting custom parts that we need.
And just so everybody knows, Corbin is our on-site fabrication specialist. He kind of looks like a member of the Hells Angels. He is a fascinating guy. He rolls up on his Harley Davidson as early in the year as possible and as late in the year as possible. Pretty fascinating guy to get to work with.
So how many of you guys are currently in high school? So a great deal of you. So the robotics club actually works with an FRC club, which is a high school robotics club, and they come here into this lab and work on their robot as well for their competition. So if you kind of want some experience at UAA working in a lab that you would be going to college for, joining the FRC would be a perfect opportunity to not only get to know, get further into engineering, but also to get to know maybe your future peers, or get to know your future environment. It's also just a great opportunity to know what it's like to work with the robotics club.
Awesome. Well, if there aren't any other questions, we'll head on to our next demonstration. So thanks a bunch, guys, for coming out. I know Tuesday nights are kind of prime study time, so thank you. They're both current students too, so they're pretty busy people.
Okay. If you've got a couple minutes to hang around, I've actually got our science platform wired up with some buttons and switches so you can kind of play around with it.
Got a little bit of flexibility in the schedule.
All right, cool.
Since we kind of merged teams. So yeah, you want to show us what we're working with?
Yeah, absolutely.
Will the online people need to kind of be able to see it as well?
Yeah, we'll need to. Is it something you can move?
It's pretty much immobile.
Okay, so if we can do this and then can kind of have maybe some folks can come around to this side to see. Get a few more bodies over here. Just be careful of that wire there.
Right. So some of you can't see this. You guys can. This is kind of a prototype setup for our science platform control system. So we've got this set up and running right now so that our science team and our mechanical team can kind of work on iterating the design while the electrical team's kind of finalizing this and putting this together. We actually have a custom board ready to be sent out to get milled right now, but the board was built to be manufactured by a Chinese manufacturer, and because of the coronavirus, we actually are having some supply chain issues. So we're kind of waiting for that to clear up. But in the meantime, we've got this really fun kind of thing that you guys are more than welcome to come and play with. So you want to come up and give it a go? So how this basically works is we've got 3 buttons here, and each of these buttons turns on or off the X, Y, and Z axis motors. I believe it's in that order. You can kind of play with it. And then we also have this set of switches here, where these last 3 switches will change the direction. So if we press this button, that makes the Z axis go down, but if we flip this switch, it is not going back up. Interesting. So one of the reasons why we're switching to a board is these are very susceptible to noise, these breadboards, and some of the electronics don't really enjoy that. So we're switching to something a little more integrated so that we can actually implement some EMF shielding. So yeah, you go ahead and try it out.
Tyler, or the robotics team designed it?
Yeah, I helped design it.
Nice.
Yeah, in conjunction with Chandra, who's our lead computer science engineer.
Cool.
Yep. So during competition, how this works is we have an external kind of grabber that picks up a sample of dirt, drops it into this, and then it funnels it into this collection bin here. And I can move this out of the way so you've got more free space to move around. And then this has a scoop on it, and we can go into this bin and take samples of soil and then bring it over to this machine over here, which does our spectroscopy and our gas sensing.
So during competition, you would be controlling this with a gamepad?
Yes. Yeah. We haven't fully automated this system yet. Yeah. So if anyone else wants to give it a try, it's a lot of fun. I come in here.
Sweet. We got a few more minutes.
No.
Okay.
All right.
Well, thanks again, guys. Super appreciate you coming out tonight. Has the other group come already?
No, you're the first group.
Okay,
Yep.
cool. So it's just, I think they can talk to you guys. There's only 2 groups now.
Oh, there's only 2.
Yeah, a bunch of people didn't show up. So
Oh, last I heard it was 4.
Yeah, so only 2 groups.
It got dropped again. Okay.
Yeah.
Okay.
Yeah, it's just I think with the roads, people didn't want to come.
What was that? Okay.
Yeah.
Okay.
Cool. So next on our little journey
I think we did all right.
which should be just this way. We are gonna
All right.
It's on now. And it's just recording for the camera?
The live stream.
All right, I'm going to have to go left hand so I can point with stuff. All right, so I'm a electrical engineering professor. This lab is for electromagnetics stuff. Generally, it ends up as a special projects area as well. So what we have on tap for display is both electrostatic speakers and then a student-built radar unit, which is on that bench that technically it's right in front of you guys. It looks like two aluminum insert horn. It's a horn. Technically, they're horn antennas. They're square. Unfortunately, it's not operational, but I have video that shows that it works. So that's what we're going to do. So in terms of electrical engineering, audio electronics have a fair amount of electrical engineering in them. These are electrostatic speakers. Hopefully this is old news and boring. But normal speakers like the subwoofers in the base of this cabinet, you have a magnet and you have a coil. The coil runs current from your audio source. Due to some forces, it shoves the baffle around and it vibrates the air. Everyone hears it. It's great. Electrostatic speakers work differently, where we step up to a pretty high DC voltage. I think these panels are up to like 2,000 volts. And that voltage establishes an attraction between the front and back plate. And then we take and we add the audio signal to that, in which case those plates start to vibrate. So we're moving air through electrostatic stuff, which is fun, I suppose. Other stuff that's not special to electrostatic speakers is the audio signal. These work really well on high frequency. Obviously, you've got a membrane that has to vibrate. So at high frequency, it can vibrate very quickly. Does very well, but at low frequency, you're trying to move a lot of air. So bass, low, when was that? I know when I was in high school, that was the thing. You could like hear the bass in the car in the parking lot all the way across campus. Is that still a thing? No one wants to confirm or deny that? All right. Okay, you can confirm that. So we have electrical components and circuits that take the audio signal in and then split it and separate it to low frequency elements. We drive that to the woofers. High frequency elements get boosted and driven to the panel so that they vibrate nicely. Other fun things with the electrostatic speakers is this is actually a plane wave coming out here. So if you've done physics experiments with waves, it's a very flat wavefront. So these speakers happen to be very directional. I'm going to attempt to turn it up a little bit. My colleague left me a selection of CDs. This is the best one. So you guys in the center should be getting the best sound of this because the waves are coming out hitting you specifically. I, who am at like 90 degrees from the thing, it's very quiet to me right here because the sound waves are all moving that way. Which is just a nice effect. The bass is technically expanding spherically as you would with a wave. So audio circuits. I'm just going to let that play as long as it's not too loud. So now the radar that's in the back, you will see that there are two horn antennas. Those horns just look like square trapezoidal beads. We're taking a 2.4 gigahertz signal, which happens to be the same frequency as the Wi-Fi band, and we are broadcasting two versions of this. We're broadcasting a signal out of one of those antennas. That signal hits an object, bounces back. We then multiply those two signals together, and we will get a mathematical function that tells us something about this. So one version of this operation would be a Doppler radar, where I'm going to try to hit play here. So I'm broadcasting a signal, well, not me, but somebody in this film is broadcasting a signal. And in fact, they're using this speaker, which is metal, which also acts as a really good reflector of electromagnetic radiation. And he is walking right now towards the unit. And you can see the frequency on the oscilloscope is displaying. Technically, that frequency is directly proportional to the speed that he is walking. So this is a Doppler unit. If you're broadcasting a single frequency, you will get at the output the multiplication of those two waves, which would be trigonometry. Who likes trig? No one? Trig. Cosine of frequency 1 times cosine of frequency 2, you get the sum and the product. And so we have the result of that. And by measuring the frequency of that, we know the speed that my student was shoving this speaker at. Of course, he was also the one filming it and then pushing the speaker, so there's some delay. He's trying to hit a constant speed, so you see the wave line up. And then he turns around and goes backwards. Also, there does happen to be a magnitude change because we're getting closer, but the actual information is contained in that frequency. I'm going to go to the other canned video here. So the other mode that this works at is as a, getting a little seasick right now, is as a distance measurement device. So what we're doing is we're linearly increasing the frequency as time moves on. So I'm currently transmitting a sine wave. It's a nice frequency. It's a single frequency. But what comes back reflected is what I was transmitting a second ago or 2 seconds ago. And if I know the rate that I'm sweeping, then I can multiply them, and then that difference of frequency is directly proportional to distance. So I'm going to try to run this again. And initially, we're starting looking at a wall, and behind the speaker, there's a pink line that's very short. That's a very low frequency. And then as we finish up and we're looking down the hallway, there's that mountain in the center of our display. That is actually the far wall at the end of the hallway bouncing back. We actually measured it out, and that was, in fact, the far wall. So with the same system, with 2 different inputs, we could measure both the speed of an object, which originally all I wanted to do was like roll this up onto the bridge and then irradiate cars with it, and then just see who's speeding, right? If it's good enough for the cops, it's good enough for us. But it was designed to be like baseball speeds. Like I want to see what the fastball is, see what the cars are. And then the ranging operation was, ideally we want to be able to scan a field and then find objects within that field. Yeah. So that, I think that's my spiel at the moment.
So this is the radar is something that you designed?
I would like to say that. The radar itself is old technology. The specific topologies that we were using is pre-existing, but then the details, I'll claim responsibility for the details. So I don't want to take credit for everything. One more show that might be reasonable. My students were also working on trying to make visualizations an option. So this is the ranging operation, and the student is taking the speaker and he's walking down the hallway. So that extremely nice colorful plot I will call a waterfall plot, because it's basically showing the top graph, which is distance, but we've now added time to the graph. So you can see the distance move back, and now he's still here, part of him, playing with this image, trying to find visualizations. But if I can point to this is time 0, and the speaker starts close, and as time moves out, the speaker is walking away from us, and then that huge mountain there is the end of the hallway, which we're always seeing. So not only are we measuring the speaker, but we're seeing what's behind it. Yeah, it's we're building this into a series of senior projects. What can we measure? What can we do? That's a learning experience.
What's the basic difference between this and radar they used in World War II to get a submarine?
So a submarine would be sonar. Functionally, nothing. Well, okay, so sonar with the submarines would be active or passive. Passive, they're just listening on a microphone for whatever's coming in. The active sonar, you send a beep pulse of sound. That sound wave travels through water, hits hopefully the nice solid hull of the submarine and bounces back, and then you're listening for the return signal. And with a sonar, you can actually measure time. So you're able to measure. You know when you send the pulse, you know the speed of water or the speed of sound in water. So the time that pulse comes back, you go echolocation, something is out here. World War II, when they first started using radar, was functionally this stuff as well. If you take this, because this radar only looks one direction, but we put it up and we spin it, and then we know I saw something when I'm at this angle. So you emit the electromagnetic radiation. Once it hits a metal object like a plane, it will reflect. We can recover that reflection and then interpret it. Distance to target, we would be sweeping this signal, which is functionally what they used in World War II. The weather radars are significantly more sophisticated. We're not there yet. I think now a lot of the modern radars are pulsed radars. And so this is continuously broadcasting out solid waves of electromagnetic energy. And then we're interpreting the waveforms when they come back, how they mix, because we know the nature they send them. High speed radars, just like the sonar, like the submarine, send out a pulse and then record the time at when it comes back. And then they know, because speed of light in a vacuum and speed of light in air, we get ranging distance from there. Similar operations on the shelf in the back, the yellow stuff is a ground penetrating radar. Same system, it's just looking down. So it sends a frequency information pulse into the ground, and every time that pulse hits a layer transmission, it will generate a reflection. Then we record that reflection to find, well, in this case, the professor who uses that goes out on ice road stuff. Go take it across the rivers, see if they're frozen, measure thickness of ice, find the freeze line, stuff like that. Unfortunately, we haven't been able to use it to find like gigantic amounts of buried gold yet, but I'm working on that.
So what would happen if you used it on sand?
There would probably not be a very hard reflection off the sand, but you would see something off of the next layer down. Of the what? Of I do. This one limited out at about 200 meters, and part of that is we on purpose, and technically it was me, to use the royal we, I did it. In order to not make the FCC upset with us, we had to limit the range of frequencies that we could broadcast in. And so that range of frequency that we could broadcast limited the distance that we could reach out and still resolve a separate object. In terms of broadcast power, the FCC, we were also limited on that. The odds that the FCC is going to be listening on an antenna around campus to catch us, probably not that big. But we're supposed to be, what's the word I'm looking for? Is it ethical? Oh, discreet. That's the right word. We're supposed to be discreet. No. So we're trying to stay within. The FCC allocates the electromagnetic spectrum. They're the ones that say, 101, 105. The Fox is 101.5, and K-Whale is 106.5, and an AM station is this, and your telephone gets to operate in this band. So they stipulate what bands of frequencies that you can use. And technically, there's a marine radar, or there's a marine beacon that's on the hillside that whenever we're measuring radio frequencies in the room, when we pick up, it's very strong. And then the military stuff, we stay out of their range, stay out of their frequencies. They don't like that.
Okay, so I guess we can now move on to speech recognition, which is upstairs. Anyone have any last minute questions? Curiosities to ask?
I got one. You're our only electrical engineering professor not in the college.
Yeah.
We have others, but here tonight. What's your 30-second spiel on why electrical instead of the others?
Yeah. Why the others? It's really a personal choice thing. Electrical engineers, we fundamentally deal with the flow of electrons, and electrical engineering is a really wide field, right? So at one end, you've got massive amount of electrons flowing, which would be the power plant. Turning the lights on, that's a fun thing. Keeping the heater going, I like that. Electrical grid transmission is that. But then we also move information through electrons, which would be the communication side of things, communication protocols, cell phones, radar. We're transmitting signals through air and interpreting that. So anytime electrons are bouncing, that's us, which I find fun. It's math heavy, it's physics heavy. It's good stuff. Yeah, that's the best I have.
Yeah, thank you, Dr. Peterson.
Yeah.
All right, you got a minute to chill out.
And again, this is Dr. Kenrick Mock, the interim dean of the college. Met him earlier.
Crazy one. Talks in the microphone.
Yeah. Yeah, we're just a little weird like that.
We're waiting for Andy. You go to openprocessing.org, you can log in and do this stuff yourself. So as this demonstration, it's a little bit about, let's start with speech synthesis. So it turns out that most computers have,
Hello there.
and making the UK voice say things that UK people wouldn't say, like French fries or something, because they would say chips instead, right? Anyways.
French fries.
And we've got a bunch of other accents. Here's our Italian one.
French fries.
Okay, so let's say a little bit about how this would be constructed. So here, this particular language is a text-based programming language. So some of you might have used more graphical languages where you have like blocks and things. So in this case, it's all in text. So let's look a little bit at how this is built. And so if I go scroll through the whole code, and so there's actually not that much code here. I know it looks like it's a fair bit, but it's really not very much. And I just wanted to walk through some parts of it, not to turn you into programmers here in the next 5 minutes, but just to give you an idea about what it will be like to be writing code as a programmer. So in this language, we can make variables. And so these things up here are all variables. And for example, this variable called message to speak corresponds to, if I go back to the program, it corresponds to whatever we've got inside this text box. So if we have something typed in there, then whatever is in there we can access through this variable called message to speak. And then there's another one here called selection voice, and then that corresponds to which voice we have picked, whether it's the UK voice or the Italian voice or whatever. And then we've got a few others. So let me say a little bit about how this thing starts. And so in this particular language, we write our code inside functions. And so we start out with this thing called setup. And the way that these functions work is it just starts running code line by line. So it'll run this line of code and then go down to the next line of code and then just work its way down until it reaches the end of the function. So there's some stuff here to initialize our speech engine. And then let me just jump down to this one. Here we make a label, and a label corresponds to the text that we can't select. It's just text that's sitting on the form. So we've got this text that says select voice, and in our browser we have coordinates where we want to put the text, and the coordinates start at 0, 0, and it's the upper left corner, and the x coordinate goes to the right, and the y coordinate goes down. So if I wanted this label to be somewhere else, then I would go to my code, and then right now that label is at position 1010. If I change it to like 110, then here we can see that it's moved it over 100 pixels over. So the first part about making this application was like laying out these different buttons and boxes to figure out where I wanted them to be on the screen. And then the second part was to make them do something. And so we wanted it so when you click on that Say It button, it actually speaks. And so I can jump down to that part. So the way that works is we create a, whoops, I need to go down here. We create a button, and then there's a function called mouse pressed, and then what we put inside the parentheses is another function that we want to run when the mouse is pressed. So whenever the mouse is pressed, it's going to run this function called say it. And so if I scroll down, that's a function that I wrote. Whoops, I went too far. And then what say it does is it goes to our speech generator, and then it speaks whatever message is in there. So we are able to write our own functions like this to organize our code, and then we can use functions that other people have built, like the speak function, to speak whatever message we want to say. So hidden behind the speak function is a whole ton of code that figures out how to say the voice and whatever text we specified. All right, so to demonstrate one more thing here, it's also really easy to do speech recognition. And so I've also got on this form a speech recognition component. And so here, just briefly, the way it works is, if I scroll up here, I made this button that says recognize speech. It works kind of the same way as the say it. When you click that button, it's going to run the function that's called recognize speech. And if we scroll down and look at what recognize speech does, it's right here. Then we start our speech recognizer, and then when it's done listening for voice, then it comes down to it runs recognize finished, and then what it'll do is it will take the result that it thinks we've said, put it into that message box, and then it will speak it right here. So here we can see it in action. So if I click on recognize speech, welcome to UAA Journey in Engineering.
UAA Journey in Engineering.
I missed the welcome part, but I got the rest of it pretty well. So it's kind of fun. I can make myself with a female UK accent. Hello there.
Hello there.
So that's this little demo. So one thing I wanted to point out is, there's a little bit of a learning curve when you're programming. But it's not. I guess it's not. I don't think it's that bad. And what I really like about it is you can create all kinds of things in this sort of virtual programming world. So there's like a nice analogy, I think, with electrical engineering and civil engineering, where you're building physical things. And you want to make sure your bridges don't fail. So you do similar kinds of things here, but it's all virtual. And I kind of like that because, you can sort of like build your bridge and test it all virtually right here. You don't have to actually build it in real life. And it's fun to build things in real life too. But you have the ability to create things and run them and test them that you can't really do with lots of other engineering disciplines. So my last thing, if you have any questions, is if you're interested in this particular language, we do have our summer engineering academies where we have a session for high school kids to basically do programming in the same language. So that's my spiel. Anyone have any questions? This one is called P5JS, but then the website is Open Processing.
And I would just add that you actually met already the instructor for that summer camp, Dr. Newmeyer. He'll be leading the high school coding camp this summer for the summer engineering academies. So anybody going into 9 through 12 could sign up for that right now if you wanted. But current seniors, you'll just have to come to UAA.
All right, any other questions? All right, is this the last one for you, or is there another one?
There's one more.
One more, okay.
Cool. Well, thank you very much, Dr. Vaughn.
All right,
Yeah.
you're welcome.
We'll be headed just back downstairs to the 3rd floor for our final demo.
Testing, testing.
So, thank you for coming in tonight. So, as I said, my name is Dr. Lauter. I'm with the Computer Science Department here at UAA College of Engineering. And today, I'm gonna change your voice in real time to Mickey Mouse. So, what does that all mean? So, first of all, do you know how they did the changing of the voice of that voice actor who spoke Mickey Mouse, say, in the 50s, so it became Mickey Mouse? Does anyone know how that worked? So when they did it in the 50s, the voice actor had to speak pretty slowly on tape, and then they speeded up the tape, and that has the effect of changing the pitch of the voice, make it highly pitched, right? Okay. You can do that if you are doing, the voice stream for a Mickey Mouse cartoon, but you can't do that in real time. So what does real time mean? It means while you are speaking, it gets changed to Mickey Mouse. Okay. And why can't we use that, record it and then play it faster and it becomes more highly pitched? We can't use that because you can't speak slowly and fast at the same time, right? If you speak it slowly and I play it back faster, there's going to be gaps in it. So I need to do something else. And what I am using here is theory developed by a French guy in the 17th and 18th century, no, 18th and 19th century, Jean-Baptiste Joseph Fourier, a poor guy, simply because he developed that theory at that time for thermodynamics. That's completely other things. That's how heat travels in substances. So he analyzed things like, steam engines at that time were high in fashion. Everyone used steam engines, and he wanted to see how heat traveled in pipes of steam engines and all these things. And he developed that theory, and no one believed him. They all said, no, 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 it doesn't work. Doesn't work. And he died poor and angry because no one believed him, but his theory does work. And that theory can be used to change your voice in real time using a computer as a real computer, so to compute things, math stuff in real time, to make it high pitched. Okay, so to do so, I brought a small computer here. So it's pretty small, costs about $50. Sitting here, really small, weighs, I don't know, 3 ounces or something. Right? And that computer is connected to the network, and it's connected to the phone network. And I will now ask 2 of you to come up here with your phones. I hope everyone has a phone. Nowadays, everyone has a phone, right? Do we have 2 phones here in the auditorium? No? We don't have 2 phones? Okay. Come on. No. Someone wants to do it, right? No? Okay, come up, please. 1 phone. And I do have a phone, of course, eventually, if it need be, but I see another phone. You want to come up? It died. Okay. You want to come up? Have a phone? No? No phone? Okay, come up. Okay. Thank you. So, one of you needs to call this Oregon number here and put it on speaker so that we can all hear it. And once you get prompted, it says something like enter the phone number now. You're going to enter Vanessa's phone number, and then the other phone's going to ring after a couple of seconds, and you're going to be connected when you get the call. But it's not going to be a direct call. It's going to go over that computer over there. So and here you see the call proceeding over that computer. And you're going to answer that phone, not on speaker, please. And we're going to hear your voice first unchanged, and then after 200 milliseconds, half a second, changed on the other phone. Go ahead, say something.
Hello? The engineering program is amazing.
Can you make it a little bit louder, please?
I can try.
Okay, say something.
Go Seawolves.
Go Seawolves.
UAA is the place to be.
Thank you, Mickey Mouse. It works in the other direction as well. So what you say goes changed in the other direction as well. Of course, we won't use a Fourier transform every day to do fun things like changing your voice. I mean, this is more for fun. But computer science is not just fun. It's also used. It's one of the professions you're pretty sure you're never gonna lose your job, or you're always gonna find a new job afterwards. At least in the last 20 years it's been so. These jobs are pretty well paid, so thank you, the world. Yes. So that's perhaps a career plan for you. And yeah, that Fourier theory is used like everywhere where computers can be found. So it's used in every cell phone of the world. It's used in every MP3 player. It's used in every digital TV. It's used in every camera that does take JPEG pictures. That poor guy, Joseph Fourier, never heard about his fame. Died poor and angry, but it does work, right? So, here at Computer Science and Computer Engineering, College of Engineering at UAA, we learn from the very beginning how to program computers, how to structure huge programs. I used to work for Intel Corporation at one point in my professional life as a software engineer. I was part of a team who wrote a piece of software that had about 1 billion lines of code, right? In a team with 200 people all working on 1 billion lines of instructions given to a computer, right? So you need to learn at some point, and we are teaching this at UAA here in College of Engineering, software engineering, how to structure a team of 200 people who need to write programs together. And you learn that in software engineering. You can do fun things over the internet because the internet is everywhere nowadays, right? Computers go like everywhere, really everywhere. So that phone on that wall is a small computer. The climate control button next to it is probably also having a small CPU unit, a microprocessor with the display, and does the climate control, the AC control here. Your car, if it isn't a car, there's like a vintage car from the 70s, has about 30 computer systems in it. Ignition control, so how you time the ignition of that gasoline engine so that the EPA finds their emission limitations, checked, and all these things. Climate control, whatever it needs to be done in that car to do these things, that's all done with computers, small and large. And if you went to UAA for computer engineering, not computer science, it was more like building computer systems with electrical engineers and mechanical engineers together that get integrated in all kinds of devices, right? Your TV is a computer, right? Everything is a computer nowadays. I don't know if that microphone is a computer. Probably it is, perhaps not, right? You learn these things, and if you were more to go into computer science is the younger sibling in a brotherhood of two sisters and brothers. The older brother is math. The younger brother or the younger sister is computer science. And of course, you shouldn't be too allergic to math, right? If you go to computer science, but it's not all math. So we do other things than math for the whole day, right? But yeah, some logical thinking is needed and required here. You can learn these things, and you can learn these things, by the way, already at a pretty early age. We have the summer engineering academies where we have Lego robotics clubs, right? Joey's doing that. And if you're a little bit older and you don't really want to go into a summer camp, but you don't know what to do in summer besides fishing, you could also enroll into a class of computer science, for example. We are offering a very basic class on Python programming. Over the summer, you can get help to get enrolled. You don't need to have any kind of prerequisite, etc. So you simply enroll into that thing, and it's good. I did my training. I'm teaching that class. I did my training. I can work with minors, so it's good. Starting at the age of 16, I think we're good. And that can count towards your high school degree, and it could also count already towards your college degree here at UAA, because that credit can be kept alive, and you can then start this fall or the next fall, whenever you're ready, to dive into computer science, already one leap ahead of all the others who didn't take the summer class. So if you're interested in that, it's really basic. You don't need anything more than some additions, and you need to know what an addition is, like 3 + 4, and that's it, right? You need to be able to read and write, and you are able to do that. And with this baggage, you can learn how to program a computer, 5-week class, and you already have something. So projects lead the way at high school can be integrated into that, and pretty good. Okay, so I said a lot of things. Now it's up to you. Do you have questions? Any questions? No questions. Do you want to try it out again and make it change your voice to Mickey Mouse. Pardon me? This phone doesn't have long distance calling, and unfortunately I couldn't get an Alaska number. So I have an Oregon number, but yeah, we can use two other phones if you wish and try it out again, or again the same phones, right? Yes, or I could answer a question. We can take photos if you wish, or if you don't wish to take photos with me. You can take your own photos without me. It's good as well, or we can look at other things. Right, great. Okay. What attracted me into computer science? I don't know. So when I left high school, I was not sure whether I could become an interpreter for human languages, or whether I should go into something like engineering. And what brought me eventually into computer science is probably my hobby. So my hobby is to collect old phone sets. So it's not a poor chance that I'm doing something over phones tonight with you, right? I'm collecting phones, and phones, before computers were invented, were actually switched already with some automatic equipment. So you could call across town or even across the country, and that number entered would be processed by a huge machinery of electrical relays and things like that, and then transmitted over an analog network at that time in the 50s, 60s, 70s, right? I wasn't born there. And the study of networks and how you can make things communicate brought me probably to computer science. Now, research-wise, I'm doing something completely different now, but sometimes it's a little bit, you enroll into a program, and then at some point a professor tells you, you're good at this, perhaps you should go there, and there's an opportunity because I can get you on a scholarship for this or that, and you go there and you end up doing your research in academia in something completely different. I'm working with numerical computing and how you can make a computer actually compute things, like huge things. Currently working on a project that we want to get financed, where we would send a satellite into space that would go over Alaska every 90 minutes, take photos, infrared photos of Alaska, and then have a computer analyze these photos for heat spots, so that these fires, like we had them over the summer last year, could be detected automatically. And that's the thing what you already can do with computers, right? It's differential equations. It's quite some math, but you can do that with computers. You can do other things. If you don't like math, yeah, you're not necessarily required to do that in computer science, but yeah, that's also part of my job to do these things, right?
Can you talk a little bit about research as something that undergraduates can participate in?
So research can be done at any age. Each time you ask a question why, and you drive your parents crazy because you ask why at the age of 3 for everything. I have 2 kids. That's already research, right? Asking questions, always being curious, and trying to solve new challenges which you find for yourself is research. So when you come in as an undergraduate here and you're in college, at some point, also professor's gonna say in class, there's this and that thing where I would need someone to perhaps try out something, program it out, and see if the computer can do it or can't do it or something. So for example, I had a student last year, undergraduate student. I wanted to get a certain problem solved. We tried it out. It failed. But that's a success. That's success in research if you can show that it's not possible to do that, right? So that the next one can already say, okay, this one is not good. Let's try the next thing. So it always keeps on going, and it's always a quest of asking why, or can we get that faster, or can we get that cheaper, and these things. That's all research. For example, who is a gamer here? Certainly a gamer among you, right? Yes. Okay, a couple of gamers. Right. So you play your games at which resolution? I don't know. I'm not a gamer. 2000 by something, right? Okay, so 2000 pixels on one row and 1000 pixels. So that's it. 2 million pixels, right? At a frame rate, so how many frames are displayed, like in a movie, of 30? Okay. 65? Okay, 65. Take it, make it 65. So that's 130 million pixels to be drawn per second. Per pixel, the computer needs to evaluate, so compute 3 divisions. So it's about 390 million divisions of numbers with about 7 digits after the dot, right? That computer computes per second. But that's a small computer which you can buy with, I don't know, how much does that cost to play a game like this? $1,000? $2,000? $2,000, right? Not more than that, okay? And it does your 390 million multiplications and divisions per second. There are computers, supercomputers, which we program also. If you know American computing, for example, the fastest computer in the world sits in California. It executes 1 billion of a billion instructions per second. So it's 1 billion billions of instruction per second. So that's a 1 with 18 zeros behind per second, right? So that costs more than $2,000, of course. But we need that for all kinds of simulations. You want to know, a biologist comes in, they understand that life is about proteins. These proteins can fold a certain way, they can also fold another way. And for example, getting Alzheimer's is also thought to be about the same protein being folded differently, right? Or why does your DNA have that helix structure? These things get simulated on computers because you can't look at these atoms it's atoms, you can look at them with a microscope. So you simulate them with computers, and that's where you need 1 billion of a billion instructions per second, and even these computations run for weeks and then give us something, right? Yeah, okay, other things. Nothing more? Want to try it out again? Mickey Mouse? No Mickey Mouse? Okay, no Mickey Mouse. Then thank you.